Here we go with the model number 4. Till here we have seen and we have discussed the topics which are related to a basic crystal structure and different types of a material, in which we have seen ferrous and non-ferrous materials and its alloys. So moving on with the discussion on the materials. So here we go with the model number 4, that is a composite materials. In the composite material, so we are going to discuss about the basic definition, classification, what are the properties, and how we are going to process, what are the advantages and disadvantages, and the application of a composite material. So to begin with the introduction to the composite material. So here we will discuss what exactly a composite material is made up of, how these things are classified, and what are the advantages and disadvantages, and what are the roles of different materials which it made up of. So when we see the composite material in the present age, in the scenario, so if you take any of the material in a day-to-day life, okay, so in engineering application, you can see they are made up of one or the other composite material. So as we have discussed even in the earlier sections, the materials, the modification in the materials is inspired by the whatever the materials are which are existing in the nature. Say for example, when we take the composite material, wood, okay, or a plant is the best example which we can give it for a composite material, where the fibers are bonded or bound by a liquid material, okay, so where they are given a proper shape and a strength with the presence of these a liquid and a fiber material. Or even if you take, okay, the eatables like a sweets, okay, so like a son papdi or these motichur. So all these things you can see there is a particle or maybe a fiber material which are bounded by a liquid solution. Okay, say now if you take any of those sweet material, sugar solution is the one which is going to bind all these particles intact and it is going to give a proper shape. So in a similar fashion, so when we see the classification of a material like a metals, non-metals, alloys, okay, or ceramics, plastics. So if you take all these categories of materials, so we have advantages and we have disadvantages. Say just to take an example, if you see the metals which are having a very good strength and they are having a high density, because of that one the weight is more. And in other words, if you take a plastics, so the strength is little bit lower compared to the metals, but when it comes to the weight, they are light in weight. And when we compare these to the metals, that is especially for ferrous metals, these are non-corrosive in nature, okay, and if they are reinforced with the proper materials, they can withstand a very high pressure also. And if you compare the same thing with the ceramic material, so ceramic materials are having a very good compression strength and a very hot corrosion resistance, but when they are compared with the tensile strength, they are weak in nature, okay. So in a similar fashion, so if you consider any category of the material, so they are having advantages and disadvantages. Then they thought like, why can't we combine or mix these metals with the plastics or ceramics with the plastics. Okay, so where we can get a advantage of both the materials. Okay, so say if you're going to mix or if you're going to have a composite material which is made up of a metal and a plastic material, so we can get an advantage like the overall weight may get reduced, the strength is increased, and corrosion nature is increased, like that. So we will get both the advantages. Okay, so if you see the present scenario, okay, just to have a glance how these composite materials have occupied the present application area. Okay, so if you see a aeroplane, okay, a flight, and if you see the parts in that one, so more than 80% of the aeroplane so called critical components are made up of composite materials. Okay, so if you see the sketch here, you can observe, so we have a carbon fiber reinforced plastic. Okay, so we have a aramid fiber reinforced plastic, and we have a glass fiber reinforced plastic, and remaining parts also are made up of one or the other lightweight composite material. Okay, so if you see all these parts which are mentioned in a different color coding are all are critical parts, so which are having a high strength and a lightweight material. Okay, so even we have seen in the previous slide, so we used to get a bicycle for a 1000 to 2000 rupees in a olden days. So now if you go and ask for a bicycle, so they will ask the price range, how much is the budget. So depending upon the budget, so they are going to give a high performance bicycles. Okay, it costs a lakhs of rupees also. Why? Because nowadays the bicycles, most of the parts of the bicycle are made up of a fiber reinforced composite materials. Okay, so where we are going to have a lightweight, and this corrosion and all is eliminated, and the strength is more, so the efficiency is more. You need not to put much effort in order to ride that bicycle. So like that. Okay, so to just have an idea, okay, so what exactly these composite material and how this has occupied the present scenario. A common example in the composite material is a concrete. Okay, so where you can see a cement powder which is mixed with the water is going to act as a binding material, and if you are going to mix the jelly stones, okay, that is the small stones in that one, so that is what normally we term in our words as a particulate composite. So in other words, if you are going to have a steel rods into that one, so then we are going to call that one as a fiber reinforced composite material. Means depending upon the shape of the reinforcement material. So these jelly stone or steels, we are going to call them as a reinforcement material, and the cement with the water is called as a matrix material. Okay, matrix is the one which is going to bind these reinforcement in place. Okay, so now over a period of time, say for example, now you have built an house with these concrete pillars, so where we had mixed this cement with the water, jelly stones and the steel bars. Say for example, after a few years, say 5 years, 10 years, you're going to take out that concrete pillar and you're going to cut in between. At that time also you can see the jelly stones and steel rods and this hardened cement. Means they are physically distinct, physically separable also you can say. They are physically separable. So, but if you compare the same thing with the alloy, when we say an alloy, say for example steel, so it is made up of iron and a carbon. Okay, but when you are going to cut a steel rod, will you find the iron particles and carbon particles which are separately or physically visible to you people? No. So that is the main difference between alloy and a composite material. So alloys, there will be a chemical reaction. Okay, there will be a intermediate bonding between the two metals or maybe non-metals and all. But when it comes to the composite material, yes, there is a interface. Okay, so there is a intact between the matrix and the reinforcement, but they are physically separable. Okay, so the best example we can give it as a concrete pillar. So moving on with the discussion. So whenever we say a composite material, one thing you need to keep in mind is, so composite material is made up of two constituents, mainly two constituents. One is a matrix material and one is a reinforcement material. Matrix material is the one which binds, and reinforcement is the one which gives the strength. Okay, and these things are physically separable and it's distinct. Okay, so that you have to keep in mind. The best example, as I said in a previous slide, it's a concrete pillar. Okay, so if you cut, so you will get. In general, okay, in a theoretical manner, we can say yes, they can be separable. Okay, they can be reused and all. Okay, but in a practical condition, there are limitations. Like when we cut these concrete pillars, we can't get back that cement which we mixed with the water. Okay, so like that. So we have a practical limitations also along with the advantages. Okay, so one very important thing to be remembered. So we need to remember whenever we hear that word composite means these two words should come to your mind. One is a matrix and one is a reinforcement, which are macroscopic in manner. Okay, so and there is an interface which separates, or you can say there is a boundary which separates this matrix material with the reinforcement. Okay, so now when we compare these things with the existing metals or alloys and all, so what it makes to stand unique in that one. So composite materials are a macroscopic combination of a two or more distinct material. So I give an example, like if you compare an alloy, that's a steel, with a composite material, so you want to see what are the materials which an alloy is consisting of, you have to go to the microscopic way. You have to go to the microscopic level in order to understand what are the constituents it is made up of. But when you compare the same thing with the composite material, it's a macroscopic. When you cut that one, so with the naked eye you can see what are the constituents it is made up of. So composite materials are heterogeneous in nature. Okay, it's not like homogeneous mixture where you will get a equal dispersion of a solute and a solvent material. Okay, so the best example is a wood, so which is a heterogeneous in nature. Okay, so as I said, one constituent is a reinforcement and one constituent is a matrix phase. So the reinforcing phase material may be in the form of a fiber, particle or a flakes. So as I said, okay, so as I gave an example, so depending upon the properties which you want, depending on that one, so one can choose the shape of the reinforcement material, so which are going to decide the properties of a composite materials. Okay, so the matrix phase materials are generally continuous, so there is no discontinuity in that one. Okay, so example for a composite material, okay, is as I said, it's a concrete pillar, so where we are going to have a steel rods reinforced in the cement material. So composite materials can be very strong, stiff, yet very light in weight. Ratio of strength to the weight ratio, stiffness to the weight ratio are several times greater than that of a steel or a aluminium. So as I said, so you will get advantages of both the matrix and the reinforcement. Okay, so you need not to choose any matrix as a plastic and reinforcement as a plastic. No, so you can choose a plastic as a matrix material and these metals as a reinforcement material. So where we'll get advantages of these things. Okay, so now when we see the composite material, which is made up of two constituents, that is a matrix and a reinforcement, what are the properties we expect from a matrix and a reinforcement? Say like when we are going to choose this as a matrix and a reinforcement, what are the functions it should perform. Okay, what we are going to expect from that one. Okay, so when you see a matrix material, so it gives a shape to the composite material. Say it's, as I said, like it's a liquid. Okay, so when we are going to pour that one to any mold cavity, okay, so it is going to take a shape of the mold. Okay, the mold obviously it is made up of the component which we want, the shape of the component which we want. So means the composite in the composite material, the matrix is the one which gives the shape to the composite material. Okay, so to keep the fiber in place, okay, so it is going to act as a binding material, okay. So means if I want to have a cylindrical shape, okay, the fiber should be intact in the cylindrical shape. So then the mold cavity should be in a cylindrical shape, and we are going to pour this molten matrix, okay, so called matrix material in the mold, and it's going to bind whatever the fibers we are going to place it inside the mold in a place. So to transfer stresses to the fiber, see obviously, see whenever we talk about a matrix, so it is the one which comes in contact with the outside surface or the environment. Okay, so means whenever we are going to apply the load, okay, or any load onto a composite material, first is the matrix which is going to take up the load, and then it is transferred to the reinforcement. Okay. So to protect the reinforcement from the environment, as I said, so that is the one which comes in contact with the environment. So it is going to prevent the reinforcement or the whole composite material from the chemical or a moisture, okay, or from the mechanical degradation, okay, or from the damage due to handling. So whenever, so we are going to handle the composite material, so we are playing with the matrix material, that is the outside material. Okay, so even when it comes to the reinforcement, okay, so now the reinforcement is within the matrix, the matrix is the one which comes in contact with the environment. So now what are the roles which we expect from the material which is inside the matrix? The first is the strength. Okay, the strength of the composite material is mainly is from the reinforcement material. So they serve additional purpose, that like resistance to the conduction, resistance to the corrosion, provide a rigidity. Say like if it is a conduction means a heat transfer through the solid or the which is in contact with that one. Okay, so there should not be any what you call thermal expansion, coefficient of thermal expansion between the matrix and the reinforcement should not be that much differ. Okay, so then we are going to have a dimension instability and all. Okay, so to have those things, so while choosing the reinforcement, one should be very careful. So reinforcement that embellishes the matrix must be stronger, stiffer than the matrix, and capable of changing failure mechanism of a composite material. So whenever we are going to have a inter or intra, okay, granular, okay, so as we use the terminologies in the metals, so similarly if the composite material, the failure of that one again is dependent on the reinforcement material normally which we use in a composite materials. So their contribution to the properties such as coefficient of thermal expansion, conductivity, etc. is a remarkable one. Okay, so as we already told, okay, so when it comes to the thermal properties, the properties which we normally expect it from the matrix and the reinforcement are going to play an important role while selecting the things. Okay. So once we see, okay, so these are the two constant, two separate materials which we are going to mix together. Okay, so when we are going to mix together, so there is a boundary which is going to separate these matrix with the reinforcement. Okay, so now the strength of the whole composite now again depend on the interface which it is going to establish between the matrix and the reinforcement. Okay, so if the interface, okay, if the wettability of the matrix with the reinforcement is more, then the interface is strong, obviously the composite material is strong. So if the wettable property of the matrix over the reinforcement is a weak, okay, so then so the interface is not strong, it's a weak, so then the fracture or the failure of the composite material is going to take place through the interface. Okay, So the strongness or the weakness of a composite material and the types of a failure which a composite material can occur is fairly dependent on the type of the interface. So what are the property normally we expect from an interface? So interface plays an important role to transfer the load from a matrix to the reinforcement. As I said, so the load from the matrix is transferred to the reinforcement. So that is through the interface itself. Okay. So composite material is strong when the bonding between the matrix and reinforcement is strong, as we say, like so if interface is strong, then the bonding between the matrix and reinforcement is strong, then the whole composite strength is high. Okay. So a strong interface results in a high strength but leads to a brittle fracture. Okay. So when the strength is more, okay, then so the brittle failures are probable in a composite material. So failures normally take place along the interface rather than through the reinforcement. So if the interface is a weak, then the failures normally take place through the interface, okay, leading to the brittle fracture. So creep, fatigue, environmental degradation, so are affected by nature of the interface. So all the strength, all the resistance which is offered by the composite material, so is fairly dependent on the type of the interface normally which we are going to get. Okay, so one should be careful while choosing the matrix and the reinforcement material and the interface which we are going to form or which is going to formed when we are going to select these materials. Okay. So now when it comes to the advantages, okay, so when you compare these things with the normal metals, non-metals and the alloys, so what are the advantages normally we are going to get it? Okay, so it's a high resistance to the fatigue and a corrosion degradation because we are going to have a combination of the material. High strength or stiffness to weight ratio because we are going to choose a lightweight material and reinforce it with long fibers which are going to give a high strength. So due to greater reliability, there are fewer inspection and structural repairs. Okay, so that is what normally is a consistency. Okay. So directional tailoring capability to meet the design requirement. Say now if we want a high strength material in a longitudinal direction or a high strength in only transverse direction. So depending upon the direction, so you can tailor the composite material. Okay. So that is the one advantages. Normally we are going to get it with the composite material. So improved dent resistance is normally achieved. Okay. So because of this what you call the reinforcement with the high strength matrix reinforced with the high strength fibers, so we can get a dent resistance properties. So composites offer a improved torsional stiffness, so high resistance to the impact damages. So composites are dimensionally stable. Okay, they have a low thermal conductivity, low thermal coefficient expansion. So manufacturing assembly are simplified because the part integration, thereby reducing a cost. So normally whenever we go with the composite material, a single integrated part is manufactured rather than placing that to forming a joints and all. So the improved weatherability of composite materials in a marine environment as well as in their corrosion resistance, durability reduces the downtime for a maintenance. Okay. So the service requirements and all are eliminated due to the improved properties that leads to the low cost maintenance. Okay. So close tolerance can be achieved without machining. So the secondary machining process, all those things are eliminated. Okay. So in order to by getting the improved surface finish, the properties in that. So what are the disadvantages normally associated with the composite material? So very important thing is the first is a high cost and fabrication are more brittle than the wrought metals and more easily damaged. Transverse properties are weak. So whenever we concentrate on the any one direction property, the properties which are in opposite direction, that is a 90° to the tailored one, so are very much weak. So matrix is a weak, therefore low toughness. So reuse and disposable may be difficult, very difficult. Okay, nowadays. So these degradation of these metals or whatever the materials normally we use to make the composite material, are play an important role. Okay, so that is reuse and disposable, difficult to attach. So that is what a simple integral part, if it is manufactured with the at a time, then it is okay. If not, joining of those separable parts and all is a difficult one. So repair introduces a new problem like a refrigerated transport and storage. So hot curing, so hot and cold curing take more time. Analysis is difficult. So whenever we are going to process these composite material, curing time, okay, and processing of that one, so is a difficult one. So many a process are not automated, are not a continuous one. So we need to wait till one product is completely processed, then you need to go for a second process. Okay, so those are the disadvantages normally we are going to get in the composite materials. Okay, so moving on with the discussion. So how exactly we are going to classify? Okay, so we know like how the composite material is made up of. So what are the properties and what are the advantages and disadvantages? So now how these things are classified? Okay, so again this is an important question where normally we'll get for a 6 to 8 marks. Okay, so where composite materials, so as we know composite materials mainly made up of two main constituents, that is the one matrix and one reinforcement. Obviously the classification is also based on those two main constituents only. Okay, so first is a composite materials which are classified on the basis of a matrix materials. So what type of matrix material normally we are going to get, okay, or we are going to use. So if you use the ceramic materials as a matrix, we call them as a ceramic matrix composites. So if you use metals as a matrix material, then we are going to call them as a metal matrix composites. And if you are going to use a polymers as a matrix material, then we are going to call it as a polymer matrix composites. It's purely based on what type of matrix material you are going to use, whether it's a metal, whether it's a polymer, whether it's a ceramic. So when it comes to the polymer, so we are going to have a two classification again in that one. So one is a thermoplastic and one is a thermoset. Okay, one is a linear chain, one is a three-dimensional network. So what are the properties and how those things are we are going to process and all. So we'll see as we proceed. So one more classification is based on the reinforcement. That is the reinforcement material which we use in order to give a strength to the composite material. Okay, so these things are classified based on the one topic or one important relation between the length and the diameter, that is a L by D ratio. Normally we call that in a composite material as a aspect ratio, ASPECT, aspect ratio, that is a L by D ratio. So depending upon the L by D ratio, these reinforcement material, okay, L by D ratio of a reinforcement material, these composites are classified into fiber reinforcement composite materials, particulated reinforced composite material, structural reinforced composite material. Okay, so if the L by D ratio is more, then those are called as a reinforced composite. If the L by D ratio is very less, then they are called as a particulated composite material. So even this reinforcement fiber reinforced composite material are classified into thermoplastic and thermosets, and structural composites are classified into sandwiched and laminated composites. So how these things are visible to you, you can see like so this is a discontinuous fiber. So if it is a discontinuous fiber, we are going to have a continuous fiber here from top to the bottom. So that is a continuous fiber. Discontinuous fiber, again we are going to have a two classification, uniformly oriented and a randomly distributed. Uniformly oriented and randomly distributed. So you can see in the picture, so the picture itself speaks like what are the difference between a uniformly oriented and a randomly distributed. So if it is a particulate composite, so we are going to have a L by D ratio, that is the length to the diameter is a less, where the diameter is more, length is a less. Okay, so this is what exactly we are going to get a particulate composite. It is similar to the solid solution strengthening, what we discussed in a strengthening mechanism for metals. Okay, so where we are going to have a secondary hard particles which are going to act as an obstacle to the movement of the dislocation. But here not exactly dislocation, but they will hinder the movement or the deformation of the matrix material, okay, by acting as an obstacle and giving the strength to the composite material. And the last one is a sandwich or a laminated. So if you want to have a strength in all the directions, okay, then you are going to have a plies, so in which the fibers are oriented in a opposite direction. So you can see in this one it is oriented in a longitudinal, in the next one it is oriented in a transverse direction. So like that. So how many plies you want, that again depends on the strength of the composite material. So like that you will get a one laminate which is made up of these many plies which are glued together and compressed in order to give a strength to the composite materials. So here also you can see, okay, so how these different types of composite material based on reinforcement are in a pictorial view. Okay, so this is a laminar, fiber, particulate, and the application of those things in a practical conditions. So moving on with, so now we'll see a few properties and a few examples for a composite material which are based on the matrix material. Okay. In the first one we'll see polymer matrix composites. So in the polymer matrix composite, so what are the advantages normally associated with the polymers? So one is the lightweight, corrosion resistance, and easily processed. Okay. And in this one, whenever we see a plastic material, so there are two kinds in this one. One is the thermosets and one is the thermoplastic. And when we look to the basic structure of a polymer, so it is made up of a monomer, okay, a single entity which are called as a molecules, okay, or we call as a monomers. So these monomers are bonded by a three-dimensional structure, okay, or a strong bonding. So in a thermosets. So because of this strong bonding, the strength and the melting point are very high. Okay, so even when we are going to melt these things or subject these things to a high temperature, these are not going to melt into a molten state. They will just decompose, or else they will degrade, or they will get evaporized rather than coming into the molten state. Okay, so means depending on the basic structure, okay, molecular structure, or how the monomers are bonded, the remaining properties are defined. Okay, so you can say well bonded with the three-dimensional molecular structure, so they decompose instead of melting. Okay, so they can be retained in a partially cured condition over a long period of time. So thermosets are very flexible. Okay, they are suited to use it as a matrix material. The example for those things will be epoxy, vinyl ester, polyester, phenolic resins, etc. Okay. So in other words, if you see the thermosets, so thermosets are having a linear change, okay, or a two-dimensional molecular structure. Here the monomers are bonded with the linear bonding. So due to these linear bonding, they are having a low melting point, and when we are going to subject them to a high temperature and all, they will come to a molten state. Okay, they will get softened. Okay, so easy to what you call shape them into a different structures. Okay, so I have a two-dimensional, so softening at elevated temperatures, resins reinforced with the thermoplastics are comprised as an emerging areas. So normally we can go with the crystalline thermoplastics also, so which are going to give a more power, okay, that is a strength to the composite material. And whenever we are going to use these resins, we are going to get a good creep and fatigue properties. Okay, examples may be LDPE, that is a low density polyethylene. So UHMPE, that is ultra high molecular polyethylene, and a PET bottles, that is a polyether terephthalene. so etc. So those are the examples. Normally you can get a one question where they can ask you to differentiate between thermoplastic and thermosets. So next category will be metal matrix composite. So here metals are having a very good strength. Okay, so generating a very wide interest areas. Okay, so with the matrix, that is a plastics as a counterparts. So high strength fracture toughness, they can withstand a elevated temperature. So corrosion resistance. Okay, so with the high temperature they can withstand a corrosion. Okay, so most of the metals used as a matrix, they require reinforcement material which need to be stable over a range of temperature. Okay, so however the guiding aspect for a choice depends on the essentially on the matrix material, so which are of lightweight and which are having a high modulus of rigidity, modulus of elasticity. Okay, so normal in application, so where it is applicable for a temperature. Okay, so with a low temperature application. Okay, so only light metals are responsive as a matrix material like aluminum or titanium, magnesium. Okay, so depending upon the application. Okay, so the temperature at which these composite materials are applied. Okay, and at what condition these things are used. So depending upon that one can choose the variety of metals as a matrix materials. So the last one we go with the ceramic matrix composites. Okay, matrix composites, where these things exhibit a very strong ionic bonding. Okay, so in few cases we are going to have a covalent bonding also. So high melting point, high corrosion resistance at high temperatures. Okay, high modulus of elasticity, and they are having a very good high compression strength rather than having a tensile strength. Okay, so wherever it needs to have a very high compression strength, there we can go with the ceramic materials. Okay, so when it comes to the application where it can withstand a high temperature. Okay, so addition to the high strength, weaker ceramics are not always been successful. Often a resultant composite has proved to be a weaker. Okay, so when it comes to the combination of these matrix with the reinforcement, so one has to choose wisely to form a composite material which leads to a proper desired properties. Okay, so in case the composite will develop a strength within a ceramic at a time of cooling, resulting in a micro cracks extending from fiber to fiber within the matrix material, means they are weak in tensile properties. Okay, so good in a compression strength, that is nothing but they are having bit harder. Okay, and they leads to a brittle fracture when they are extended to a the load which is beyond their limit. Okay, so these are the classification based on a matrix material. So one can choose wisely depending upon the application and the properties. So in the coming section we will see what are the classification based on the reinforcement and what are the properties in the things. Okay, so thank you. Okay, so thank you.